All right, we should be recording. So this is the evaluation lecture. This is the one that I hinted is the most important lecture of the semester. I'm glad you're all here. Let's talk about evaluation. Quick administrative things. Homework 0 grades should be out, so you should be able to see your grades. Everyone who submitted something got 100. Some of you got more than 100, so this one was quite simple. Homework 1, I just showed you the solutions, so if you're watching this online, come to lecture next week if you want to see the homework 1 solutions, the homework 2 solutions, etc. And yes, homework 2 is due in 1 week, and then homework 3 I'll show you today, that's due in 2 weeks, so the same pattern as usual. Any other administrative questions before we get started? Okay. This is what we're going to cover today. So the first thing is about validation. Specifically how to split the data and when to split the data, how much to split the data. And then the second thing is the actual math part. As usual, the math is not important. You don't have to understand it. There's built-in functions for all of these, but there are some things that I would like you to understand, like if I tell you precision is 0.9, you should know if that is a good thing or a bad thing. So that's the level of understanding that I would like to see. And if we have time at the end, I'll quickly cover hyperparameter tuning. Okay, so validation, how many splits? The whole purpose of the entire lecture today is basically understanding the quality of a model. So if I give you a model, I would like to be able to communicate with you how likely the model is to work. That should be an obvious thing. You should want to know this information. If I give you 10 models, you should be able to figure out which one of these models is best. And spoiler alert, most of the time it's not just one. Usually there's ones that are better in certain situations. So when is this model good? When can you trust it? And when should you use a different model instead? You might also be interested in knowing when the model is likely to make mistakes and why it is making those mistakes. And then, of course, with any kind of geospatial problem, you might train it on some data, but you might be interested in making predictions somewhere else with completely different data. So how different can that data be? Can we make some assessment of how likely the model is to work under different time conditions, different space conditions, different sensor conditions? So the short answer is we'll just try it and see if it works, right? That's the qualitative approach. This is something that you should always do, but this is not great. There's a lot of things about qualitative analysis that are very subjective. If I load up my favorite language model and I ask it a question and it gets it right or it gets it wrong, that does not really tell me if that model is good or bad. That tells me if it's good at this one specific question. If I sit there and ask it 10,000 questions, I might get a better idea of whether or not this is good, but we really want a mathematical way of doing this that is independent of the person asking the questions, independent of your own understanding of right and wrong, and works more objectively. The other thing that you'll notice is no matter who it is, whether it's a big company or an individual researcher, people don't lie, but they do pick results that make them look good quite often. So if OpenAI comes out with a new language model, they're going to show you examples of look at all the cool things it can do. They are unfortunately not going to show you examples of look at all the interesting mistakes that it makes. And as researchers, those are often more interesting than the successes. We are really interested in studying when it makes mistakes and why. What we can do instead is do quantitative analysis. So this sentence is really important. Numbers don't lie if they are done correctly. I'm going to show you how to do them correctly and incorrectly so you know how to spot the difference. But this really gives us a way of mathematically measuring the likelihood that a model will make the correct predictions. But in practice, you usually want to do both. So sometimes you'll get quantitative numbers that say, oh, all the models are approximately similar. But then when you start looking into the qualitative details, you might find that some are just making the average guess every time. Some are completely ignoring certain classes that aren't important. Some are losing edge features or details and giving you really blurry results. So both of these are really important. You should always do both. quantitative is the one that you should trust more, whereas qualitative is really useful for debugging and understanding and explanation. Before I go to the next slide, is anyone afraid of insects? Okay, cool, because I have a picture of one. So this is actually based on a true story. So the first semester I taught this course, I was out hiking during the semester, and I actually did get bitten by a tick. And I found it like the next day, I removed it. And I started thinking to myself, what are the chances that this tick has Lyme disease? So I actually found, these are real numbers, I didn't make these numbers up. Lyme disease affects about 0.1% of people in Germany every year, so it's not that common. There are tests for it, and they have a 90% sensitivity and a 97% specificity. And I haven't explained what those mean yet, don't worry, I will. So that's the based on the true story part. The rest is not true. I didn't actually take a test, but let's say I did. So I took this test with this specificity, this sensitivity, and it said, you have Lyme disease. What are the chances that I actually have Lyme disease? And I won't give you enough time to sit here and do the math, but I do actually want to see what kind of guesses you have just based on intuition, gut feeling. So how many of you think 0.1%? 2? 3%? 10%? 50%? 90%? 97%? 99.9. Okay. I don't know if you noticed, but we have exactly 2 votes for almost every single one, so it's completely randomly distributed. No one has any idea. And this is kind of important, right? Like if you get a medical test and it tells you you're sick, you should have the math skills to know whether or not you're sick. This should be something that's taught in middle school. Everyone should know the answer to this question. But as we've seen, no one does, because we don't know what these terms mean. We don't care about the details. We just want to know if we're sick. And usually the doctor will do the math for you and tell you whether or not you're actually sick. But in this case, we have a test and it says we have Lyme disease, and we have absolutely no idea what the chances are that we do have Lyme disease. So in this lecture, I'll teach you what all of these things mean, sensitivity, specificity, and I'll teach you how to calculate this at the end of the lecture. So this is our motivation for the day. Okay, so I want to start off with some definitions that we're going to refer to. Yeah.
What was the answer?
I'll show you at the end. So there's some definitions that we would want to use. And these are very commonly used in all of statistics. So if you've taken a statistics course, this should be review. Population, that is everything that you are interested in. So if I am studying trees in Germany, the population is every single tree in Germany. If I'm interested in studying trees, the population is every tree in the entire world. So you can select a subset for your population. You can define what your group of interest is. If you're studying people, it could be all people. It could be all people in one country, all people of one ethnicity, all people of one religion. Now, in almost every case as a researcher, you don't have access to every data point. You can't actually study every single tree, every single person. But in order to make conclusions about the population as a whole, we will take some subset of that population that will be our sample. In best case, this sample is unbiased and representative. This smaller set of 100 trees perfectly represents every single tree in Germany. Now, depending on your sample size and where you're getting this data, that's almost never the case. Usually, if you're doing like a field study, you go to places that are easy to get to, so places near roads or places near train stations. That's obviously not going to be representative, so you have to be careful of this. But the goal is that the sample is as close as possible to the entire real data distribution. Now, this term that you're going to see, and it's going to haunt you for most of the semester, overfitting, there's different ways to describe this, but the way that I describe it is when your model tries so hard to fit the data that you give it from your sample that it stops learning things about the population. So what does that actually look like in practice? If I'm training my model and I use it on a specific set of data that I'm looking at in my sample, and then another set of data outside of my sample that it's never seen before, somewhere from elsewhere in the population. If both of them have really low accuracy and high error, that's probably a sign of underfitting. I haven't trained my model for long enough. I can train it for longer. I can try a fancier model that can learn more details. If both training and testing, both the sample data and the out of sample data have low error and high accuracy, great, we're done. We have a perfect fit. And the overfitting case is when the training accuracy actually continues to get better and better, the error gets lower and lower, but all of a sudden the error on the out of sample, out of distribution data starts to increase. The accuracy starts to decrease. That is not good, and that is what we call overfitting. Almost all of the time, your model should probably do better on training than on inference on unseen data. The question is how much, and can we control the difference between the two?
This is more related to the number of subs that you take, to the diversity between them.
Both are really important, and I'll explain some of these things throughout the entire lecture. Those are both really important. You have to get enough data and enough diverse data. And there's bad things that happen when you don't have both of those things, and I'll talk about those today. This all feels very abstract because it's all definitions. I can show you some pictures of what this means as well. So the top row is a case of classification. So let's say you've got these orange and blue pixels, and your goal is to learn some sort of function that separates these two. In the top left case, guess what? We've done a perfect job. We have 100% accuracy. We always make the right choice. But is there any real physical meaning behind this line that we learned, or is this relatively arbitrary? If I get a new data point that's right here in the middle, is it actually likely to be blue, or is it more likely to be orange? It's really hard to tell. So there's a high chance that we're overfitting. We're trying too hard to fit the data that we've given it to the point where it's starting to get worse at the real problem at hand. On the other side, if we do just a straight line, you notice we're making a ton of mistakes. It's a little bit too simple, so this is likely to be underfitting. And the right fit is some balance between the two. So it's not as complex as the first function. It doesn't have like x cubed, x to the fourth, x to the fifth, etc. It's just relatively simple, but it does a good job most of the time. The regression one is even easier, I think, to see. So in the bottom left example, we're really trying hard to perfectly fit every single point in this function. So imagine you're trying to fit CO2 data. There's noise in real data, and this model is actually learning noise. It's not learning features anymore, so that's not great. On the right side, it's just doing a straight line, but as a human, we can see it's actually closer to the one in the middle. So you want to learn a representative function, a representative model for making predictions. You don't want to learn noise, and real data always does have noise. Another example that I like to see, when people started doing computer vision research and started exploring explainability of models, they started to notice that the mistakes that models made actually taught you more about how the model worked than when it got things right. And this is one of the more famous examples. When they started looking at very large data sets, they realized that the model would usually predict Siberian Husky for the image on the left and Golden Retriever for the image on the right. And if you know dogs, you know that it's actually the reverse of that. These are wrong. So why did it get them wrong? You can actually interrogate the model a little bit and basically figure out which pixels it's looking at to make this prediction. And what they found was, it wasn't looking at the dog at all. It was looking at the background. And most of the time you see a Siberian Husky, it's playing in the snow. Most of the time you see a Golden Retriever, it's playing in the grass. So it's learning the noise of the image, it's learning the background, it's learning the unimportant details, because most of the time that works. That's sufficient to make the right prediction. So you have to be really careful with having a large enough data set, a diverse enough data set, and also you have to look out for mistakes like this. The model can learn things that you didn't intend it to learn, that humans also wouldn't learn. Okay. Now I'm going to use this term accuracy or performance throughout the lecture. For now, these are just generic terms if the model is good or bad. Later, I'll actually define these mathematically, and you'll see there's actually many different kinds of accuracy. But for now, we would like to know how well this model will work on data it's never seen before. If I train a large machine learning model on my data set, it's really not hard to get 100% accuracy. In fact, most of these models are plenty big enough to just memorize the entire data set. So there's been really interesting studies where people took data sets like MNIST, which is a collection of hand-drawn digits and correct answers, and they just randomized all of the answers. So the image and the answer have no relationship whatsoever. And if you give it a big enough model and you give it enough time, it can still get 100% accuracy because it's not learning, it's memorizing. So we want to figure out how to teach a model, not just make it memorize. And we also want to figure out how likely it is to succeed. So for instance, a good analogy on this. If I give you a test and you take the questions home, you do it, you turn it back in, I tell you which ones you got it right or wrong. And you come in next week and I give you the exact same test and the exact same test the week after that and the week after that. Eventually, you're not even going to need to look at the questions. You're going to memorize the answers. If at the end of the semester I give you a new test that has new questions, it's useless. You haven't learned anything. You just memorized. So we would like to see how likely the model is to work on questions or data that it hasn't seen before, not questions that it has seen before. Whether or not you can memorize, I don't care. Whether or not you learn something, that's what I want to know. So has our model actually learned? How do we do this? We take part of our data set, part of those XY pairs, and we save them for evaluation. You can do many different percentages for splitting this. Basically, the result looks like this. So if we have n data points in total, we'll save m of them for testing and then the rest for training or vice versa. So usually somewhere between 70-30 and 90-10, so 90% training, 10% testing. Those are all good ranges. The exact values don't matter too much, although I'll explain in a second. So this goes back to your comment earlier. Do we just need more data? And now the question is even more complicated. Do we need more training data or more testing data? And what are the trade-offs between the percentages that we have? So having too little of training or testing data is both bad, and this is what happens. If I don't have as much data to train the model, I end up with more model parameter variance. As in, the model is learning something, but if I just switch out one image, it's going to learn something very different. That's not good. We would like a model that is robust, that always makes similar predictions regardless of which iteration it's on, what random values you used. So you want enough training data so that your model converges. It's not just kind of going in a random direction. And then similarly, if we don't have enough test data, we see variance now in our performance statistics. So if I give you 10 questions and there's no partial credit, you get 90%. If I give you 10 more questions, you might get 80% just because you got unlucky and you hadn't seen that question before. That's a huge variance. Your grade should not go up or down by 10% just based on luck. That's what happens when you don't have enough test questions. If I give you 1,000 test questions, you're probably going to get approximately the same score every time that you take this test, assuming you're not learning in between the stages. So you want to have enough training data and enough testing data. If you really want to check whether or not you have enough, you can actually train the model or evaluate the model multiple times and see how much the performance metrics vary. But usually we just say, like, if you don't have a lot of data, 70-30 is probably better. If you do have a lot of data, 90-10 is probably better. Training is usually more important. You want as much data as possible to learn a very good model. You just need enough data to evaluate the model at the end. Okay, so if we want to know how good our model is, we save some data that it's never seen before and we test it. And that's how we get an accuracy. So that's how we learn our parameters. We learn them on the training data, and then we evaluate performance on test data. What about our hyperparameters? Now, I mentioned this earlier, I think in 2 lectures ago. Parameters are the things that the model learns. So for example, in our linear regression, that would be the slope and y-intercept. These are learned automatically by the model. You start out with a random guess, and you go in the direction that minimizes your mistake, and eventually it learns a good value. Hyperparameters are these things that you set before training that can't be automatically learned by the model. If you remember the SVM model that we talked about, that was the kernel function that we're using, such as linear, sigmoid, RBF, etc. There's a bunch of options there. And a lot of the models that we're going to learn towards the second half of the semester, the deep learning models, have even more hyperparameters. So how do we know what values are good for these? We could do the same thing that we just did here, where we try a random value, we train it, and then we test it. And then eventually we will find a good value. But there's yet another problem of overfitting here, where if we do this, if we try enough hyperparameters, we can find one that we get lucky on the test set. We don't want to get lucky. We want to see how good we actually are on completely unseen data. So we don't want the test data to bleed into the training data, either through the model directly seeing it or through the hyperparameters indirectly seeing it. So we can do the exact same thing we just did and make yet another split. So now the training split, the training subset of our data, is used to train the model parameters. And then there is a smaller validation split that we use to evaluate performance on this set of hyperparameters. We do that for all of our models, and then eventually we choose the one with the best results on validation. And then one last time, we evaluate performance on test to get a completely unbiased number that we can report in our research. Again, you might see 60-20-20, 80-10-10. It just depends on how much data you have, how much variance there is in your model or in your performance metrics. Here's the same thing in picture form. But most of the time, most of your data is reserved for training the model and learning the parameter weights, and then the rest is for evaluating the performance of the model. You can also train on your training data, evaluate on your validation data, do that for a bunch of models, and then figure out what the best hyperparameter is, and then retrain on all of training and validation before you report your test accuracy. You might get another 1% accuracy or something like that. That's a common practice. But most of the time as researchers, we're too busy to care, so we just do train, val, test, done. Are there any questions on this? Because it's about to get much more complicated, and I want to make sure this part at least is clear.
Maybe just one question. Is there any differentiation between who gathers the data? Because coming back to the beginning, we still have this issue of all of this is what we define, and it's not like in this sense it can still be subjective because I don't know. We said when we go to a land cover classification, we said this is savanna and this is grassland, and we define okay for us subjectively that's the difference.
Yep.
Is there something where we say okay there's an external data source which also has the issue of definitions? Do they have the same definitions as us? But is there any way to test that as well?
Yeah, that's a great question. So I think the question is basically, how do you test the accuracy of the correct answer? How do you know that you can trust your model? How do you know that you can trust your data? Is the ground truth, the correct answer, is that actually correct? And the scary part of reality is that it's never 100% correct. It always depends on the quality of the people collecting the data, the quality of the labeling, the quality of how obvious different things are. And also it depends on which classes you choose. So if you're doing land cover mapping and you've got forest, urban, savanna, grassland, savanna and grassland are very similar. Like you're going to make that mistake quite often, whereas you're not going to make a mistake on urban versus forest. They're quite different. So these are all real questions that you should always think about, especially when you find someone else's data set. You should take a look at it and see, does this look right to you most of the time? There's also going to be a lot of ambiguous things. So I showed these cute pictures of dogs here. It's pretty obvious that the correct answer for the picture on the left is golden retriever or dog or whatever. It depends on your classification. Technically, snow is also right as well, right? But usually we pick the main thing in the middle and that's the correct answer. But what if there's multiple main things in the middle? Which one is the most main? So I think it's the first computer vision lecture. I talk about the ImageNet dataset, which is this gigantic dataset with millions of images labeled by humans. And ideally, it would be 100% accurate. And there was one crazy person who said, you know what, I'm going to take this dataset and I'm going to test myself and see how good I can do as a human compared to some of these machine learning models. And they did not get 100% accuracy, they got 95% accuracy because humans also disagree with each other. So there's not always one correct answer, and even when there is, it's always difficult to tell. Especially something like land cover mapping, if you're looking at a satellite image of the Earth, you're gonna have pixels that are on the boundary between things. Which side should it be in? We may never know. So the accuracy of your data set is the most important thing. If your data set labels are only 90% accurate, you cannot train a model that is more than 90% accurate. That's a strong statement. There is a lot of research in semi-supervised learning that does weak supervision, where your labels are sometimes correct or you have labels for a subset of your data. But it's a good rule of thumb to assume that the more inaccurate your data labels are, the less accurate your model can be. Your model is limited by your data. If your model doesn't work, unfortunately, a lot of the times is collect more data or collect better data. Okay. And there's probably a way to test it, but usually it ends up being hire more humans to try to label these and see how often they disagree. Especially for language models, if you're translating a sentence to another sentence, there's not really one correct answer, and it's not really easy to mathematically measure how close you are to the correct answer. So a lot of times you just need humans to evaluate it and get a bunch of them to evaluate the same one and see, do most people agree with this or not? Okay. So this is train val test split. This is what you would use most of the time, especially for deep learning. This is really, really commonly used. But there is a problem with this approach, and it's that these kind of hard splits where some of the data is only for training, some of the data is only for testing. If you don't have a lot of data, which is unfortunately very common in Earth observation, what do you do? How do you deal with limited data? So what we could do instead is what's known as exhaustive cross-validation, where we basically try every possible way to split the data and evaluate all of them. So we're not going to get unlucky. We're not going to say like, oh, some of our testing data is much harder than the training data. That can't possibly happen now because all of the data is sometimes train and sometimes test. Now we're actually training on part of the data and evaluating on the other part for all possible combinations, and we can't have that kind of data set bias anymore. There's a couple different ways to do this. So the simplest one is leave one out. This basically means if you have n data points, train on n-1 and make a prediction for the one remaining data point. So that prediction accuracy is going to be very noisy. If you average it out over all possible test points, then it's going to be more reliable. So that kind of looks like this. So I train on everything in red in the top row, and I make a prediction for the one remaining test data point, and then I throw away my model and I start from scratch and try again on the next row where I train on everything except the second data point, and then I test on that data point. So it's a different model each time. You can probably see where this is going and why this is really slow. Another way to reduce the noise of this is to leave P out. Not just one, but P data points. So now you have this ugly formula for the number of models, and you're training on n minus P data points each time. So now your single prediction is not as noisy, but there's still a lot of different ways we could split this data set. Instead of training one model, now I'm asking you to train 1,000 models. That's not fun, that's very time consuming. So that's one of the problems with this approach. And then there's a picture of what this looks like. They don't have to be adjacent, they could be one data point here, one data point over here, one data point over here, and that would be my P data points. Okay, so people don't usually do this because it's too slow, although it is quite accurate and it does give us more nice mathematical guarantees. So what can we do instead? That's too slow. We can use non-exhaustive cross-validation to basically approximate this. And one of the most common examples is k-fold cross-validation. So here, if you have n data points, you decide, I'm going to split my data up into 5 chunks. And I'm going to train my model on 4 out of those chunks and test on the 5th one. Now I only need to train 5 models, and I'm going to use the same splits every time. So it's not every possible way to split it, but technically I am training or testing on every data point at least once. This is what that might look like. So you see the gray row, that's the predefined splits for your data. So you take all of your training data and you split it up 5 ways. And then at each time, you try one of those splits for testing, the rest for training. You measure the accuracy, and then you start over again on the second row with a completely new model with random weights. And then once you find one that works best on all of the training and validation data, then you save those parameters, you save those hyperparameters, and you try to evaluate it on your test data. You could also do the same thing for the train test split or just the train validation split. It's up to you. It really depends on how much data you have, how much time you have. But in general, the more diverse ways of evaluating your data set, the more reliable the performance metrics are, the less variance there is just from a few really hard examples in your testing data versus your training data. Okay, so that's everything to do with ways to split your data. You can do 2 big splits, 3 big splits, 5 big splits that you rotate, etc. Everything else I'm going to show you is some variation of those 2 things. Now, the other question that I have is, how do we assign values to those splits? If I've got a data set with 1,000 data points, which one should I put in train and which one should I put in test? It really depends on what you're trying to evaluate. So our data is definitely not evenly distributed. If I'm doing something like land cover mapping, maybe there's more forest than there is urban areas, or more agriculture than there is grassland. How do I make sure that my estimated accuracy is actually representative of the real world? I could end up in a situation where during training I only see cities, and then during testing I only see non-cities. And that's not going to work very well. The model's going to have no idea what it's doing. So that's not great. So how do I make sure that our data is distributed well? It depends on what we're trying to measure. So am I interested in knowing the average expected performance on new data? Am I interested on accuracy, especially for less common classes? So like if I'm doing agriculture, there's certain things like wheat and maize that are very, very common. There's also things like cashews and beans that are much less common, but those might be the things I'm more interested in. So I want to make sure I'm working well on less common classes. Am I interested in out of distribution performance or future performance? So most of the time in Earth observation and most of machine learning really, there are places with data and there are places without data. Europe and North America tend to be very data rich. The rest of the world is very data scarce. The rest of the world is oftentimes the place we're more interested in studying. So if we're interested in something like food security, we might really want to do Earth observation for agriculture in Africa. Unfortunately, we don't have any labels to train our models, so we can train them in Europe, but do European fields actually look like African fields? Do they have anything in common? Not necessarily. So we might want to know how accurate will our model be when we try to make predictions on a place that it's never seen before during training, or for a time it's never seen during training. So if I'm studying weather, I can model things like CO2, I can model things like wind speed, I can model air temperatures, but the average distribution is also moving over time. If I try to predict what weather is going to be like in 100 years, if I don't tell it that the entire Earth is warming up, it's not going to make good predictions. So we also might be interested in predicting the future. That's another way to divide things. So I want to make one other definition that we're going to use for the upcoming slides. There's two different categories of data. You can categorize your predictions. So these are our output labels. That's the thing we're trying to predict. If I'm trying to predict land cover types, those could be forest, urban, agriculture, ocean, etc. Those obviously have groups that we can bucket them into. I might be interested in making sure those groups are balanced in training and testing. You can also think about categories of your input data of your features. And this is more where the geographic or time distribution matters. So if I'm studying forests, the forests in Europe versus the forests in South America versus the forests in Australia, these are all very different. They might even have some of the same species of trees, but the distribution's going to be completely different. The background's going to be completely different. So these are different types of inputs, different categories of inputs. Is this distinction clear? Because I'm going to use this for like the next 5 or 6 slides. The difference between classes and groups. One is categories for the answer. One is categories for the question. Okay. So, how do I measure my average expected performance on data I've never seen before? This is actually relatively easy. I can just randomize everything. So if I have 1,000 data points, save 200 for testing and 800 for training, and we're done. It doesn't really matter which one is which. We definitely don't want to go sequentially because maybe we collected data here and then here and then here. We want to randomize it. We want to shuffle it up, mix it up. Just like if you're playing cards, you want to mix up the deck first. Otherwise, you might get things in order. So we're randomizing everything. We're ignoring all these classes and groups. Not important. You get something like this. So during each cross-validation split, if you're doing k-fold cross-validation, you might end up with splits like that. Or if you're just randomizing everything, you might end up with only the top row, and that's your train test split, and you're done. Both are valid solutions, depending on how much time you have to evaluate models. You can also shuffle during every epoch. If you're training your model multiple times, you can shuffle within the training data. You can't shuffle which is training and which is testing, but you can shuffle the order in which you see the questions. So for example, if you've ever taken a language course and you've had to memorize like this word in English, this word in German, if you always stare at the same list, you might have also noticed this. You start to say like, okay, I memorized the order of the questions. After this one, the next word is always this. I don't even have to look at the input anymore. That's obviously not learning, that's memorization. So maybe you start going backwards through the list, and then you start remembering the other order. Ideally, you would shuffle these up every time. So it's a random one. They're completely independent. Okay. So that's the simplest one. If I just want average performance, if I don't care about the details, this works. It's easy. I actually just gave an interview yesterday for someone to join our lab, and I asked them, how would you split your data if you wanted to make your own data set? And they just said random split. And that's not really the right answer. The more correct answer is it depends on which of these things you're trying to do. But the better answer is what we're going to see next. So you can do better than random most of the time depending on your data. Okay. When we're looking at real data, usually there is something called class imbalance. Some things are more common or less common than others. If we want to gauge the accuracy on some of these less common classes, we would hope that we see this just as often during training as we do during testing. So we can ensure that there's a balanced distribution in both training and test by splitting based on the class label. So then you get something like this. You end up with a little bit of the first class in every split, a little bit more of the second class in every split, and a lot more of the third class in every split. So this guarantees that it's basically the same distribution every time. The model isn't going to learn, oh, I've only seen urban areas, so I'm just going to predict that the answer is always urban. It's going to say, I've seen urban 1/3 of the time, but I've seen forest 2/3 of the time. So if I have to guess, I'm going to guess forest 2/3 of the time. So this makes sure that you have similar distributions every time. Again, you can shuffle within each class every time if you want to. That helps randomize the order of the questions, the order of the data. Okay, this is, in my mind, the best. Again, it depends on what you're trying to evaluate. If you want to know how likely the model works on data it's never seen before, you're likely not interested in the tree next to the one you've seen before. You're interested in a completely different location. So if I train my model in Europe, is this going to work in South America? Maybe. Let's find out how much. So what we can do is we can measure out of distribution performance, how well does the model perform on an entire region or type of data it's never seen before. Now we can split based on, for example, geographic groups, and we get something like this. So now if you look at the bottom row, that's the group. Let's say that's the country where the data is from. Now we're ensuring that one country is either in training or in testing, but not both at the same time. So for example, if I'm doing agriculture for the entire world and I've got one model to make land cover maps of agriculture, I can train it on every continent except for North America and then measure my performance on North America. And then I can switch to a new continent and see how it works on that continent instead. And that's also a good way to see like which continent is most different in terms of this thing I'm trying to measure, which one has the lowest accuracy. You can combine this with stratified and groups, and you can use many of these things. So you can actually do both, and that might be useful for some applications as well. Yep.
Is there also a way to say, I'll take samples from, I don't know, each and every country, just a couple of points, and then I can tell it to not take those that are clustered in this one region, but like single ones from each of them, so they have like a more variety distribution, that it's not one complete data set from, I don't know, Nigeria, and another one,
Yep.
so there's one data one from Costa Rica.
Yeah, there's not like a specific name for that. There's not a built-in scikit-learn. So all these happen to be scikit-learn splitters that you can use. There's not a built-in one for kind of ensuring a balanced distribution where you don't have clusters of data, but you could make one. And as long as you justify it well and you explain why you did it and really understand the purpose of this. So like, for example, I do a lot of foundation model research. And the goal is to develop one model that works well everywhere. If I want to ensure that something works well everywhere, I have to test it on somewhere it's never seen before. It's probably been trained on data from the entire Earth, so I need to save some data that it hasn't seen in order to see how well it works. If I'm only interested in one region, I don't need to do that. I can say my model only works for Europe. Don't use it outside of Europe. It's not going to work. It's never been tested, that we have no idea how well it works. That's also fine. But you have to really carefully think about what your goal is. What is the scope of the problem you're trying to solve? What are the limitations of the way you're trying to solve it? And what is the correct way to assess accuracy on real data, on real unseen data? So this is one example I can split by, for example, country. This is actually from a paper I published where I was interested in plate tectonics, but I didn't want one plate to be in both training and testing. I wanted to see how well the model works on a completely different plate it's never seen before. So I actually did a plate tectonics split. For this specific paper I wrote, this got rejected and they didn't like this. And the reason they didn't like this was because the Pacific plate was huge. And it just so happened that our model predicted that the entire Pacific plate is one big anomaly. And in reality, that just means the Pacific plate is different than the other plates. If I don't see that during training, of course I'm not going to do well. What I should really do instead is more of a grid-based approach where I'm not completely ignoring the plate, but I am avoiding nearby pixels. So there is geographic dependence between nearby points on Earth. If I measure the depth of the ocean at one place, if I go 1 kilometer to the left or right, it's probably going to be similar, right? If you measure CO2 today, it's probably going to be pretty similar tomorrow as well. The other thing that you'll notice here, the Pacific plate is way bigger than all the others. The Antarctic plate and the North American plate are actually quite small, and this is an artifact of the Mercator projection that we talked about last week. The other thing that we changed in this paper is we did latitude weighting. So basically we said these big pixels near the Antarctic, they're actually not very big. We shouldn't count them as much as we do pixels near the equator. Those are actually bigger. So you might have to weight your evaluation metrics, which we'll talk about later. This is the more commonly used grid approach. So you take a location, this is in California, and you just chop it up into a big grid, and you randomly assign grid cells to different train validation or test splits. And that's quite commonly used as well. So these are all different ways to split up that kind of data. The other thing that we talked about was time series data, especially with homework 1. A couple of you actually came to me and said, I did all this work to do train val test split, and I measured the accuracy. And I looked at it, and they were doing a random split. They were randomly assigning certain weeks or days to training versus testing. If I'm trying to predict the CO2 levels 3 years from now, and I just make a random number, it's probably not going to be very good. If I try to predict the value 3 years from now, and you tell me what the value is going to be the day before and after, it's not hard, right? You could just pick something in between. So if you're trying to make time-based predictions, you have to also ensure that your model has not seen this time before anywhere nearby. You can basically do what's called a sliding window approach, where you take from the start of your data set, let's say the bottom axis is now just the time axis, you take the first month and then you predict the next month. And then you take the first 2 months and then you predict the next month. You take the first 3 months and then predict the next month. And you basically slide forward. So the model's never seen the future. It doesn't have access to future information. It can't predict the future just based on knowing the answer. It actually has to model the past and see how it will evolve in the future. So this is the correct way to split data when you're training a time series model. And again, you can also combine this with some of the other things that we've seen before. Okay. We're perfectly in the middle. We could stop for a quick 5-minute break. There is a lot of stuff left. Do people want to take a 5-minute break and stretch their legs and wake up? Or do they want to finish up and get home early? I don't want to make you stay late. No one's brave enough to throw everyone else under the bus. I'm going to continue. Feel free to walk around and step out if you need to, but I do want to try to finish at 5. Okay, so we've talked about how to split the data, how to make a train val test split, k-fold cross validation. Those two things you should probably know. We talked about how to assign data to each split. So we talked about geographic splits, time series splits, stratified or group splits. These are all valid ways of doing it. Now, let's say we have a split. We have data for training, data for validation, data for testing. I can train my model and I can make predictions, but how do I actually compare those predictions to the correct answer? No idea what that sound was. How do I compare my predictions to the correct answer in a mathematical way that tells me how likely the model is to work? It turns out there's many different ways to do this, and it depends on what kind of problem you're trying to solve. So most problems in this course can be broken down into, is this regression or is this classification? We'll also talk about things like object detection, that's really just regression. Semantic segmentation, that's really just classification. You're usually trying to predict either a number, which is the regression example, or a category, which is the classification example. If we're doing regression, then we have some sort of input x, and the function we learn makes a prediction y, and that y is just any real number. It could be one number, it could be 10 numbers, it could be a whole image full of numbers, but the goal is to predict a number, and there's not really any constraints on that number. For example, CO2 levels, they could technically be 1 million. I think it'd be very scary if they were, but there's no upper bound that is like not allowed to be predicted. What about multidimensional input? You have a few different options here. So if I give you a number 5 and the correct answer is 6, you can tell me how close I am. If I give you 2 numbers and there are 2 correct numbers, you have a few different options for telling me how close I am. You could report each dimension separately. So let's say I'm predicting wind speed and temperature. You could say your temperature is, 3 degrees off, and your wind speed is 3 kilometers per hour off. Or they could be different. There's no guarantee that they'll be similar numbers. So I could give you an accuracy or a performance metric for each dimension. I could average all the dimensions. This definitely wouldn't make sense for something like temperature and wind speed. They have very different scales. But it might make sense for horizontal wind speed and vertical wind speed. They should be comparable. So we could take the average across all dimensions. And then we could also do a weighted average. If some are more likely to vary than others, we might be more interested in the ones that are more likely to vary. Okay, so what are some ways of measuring the performance or measuring the error of our predictions? The simplest one is error. If I tell you the correct answer is 5 and you tell me 6, then you're 1 point away from being correct. And you could do that for 100 examples, and maybe the average is 1.35. And that would be your average error. Usually we don't care about the sign here. So sometimes it's going to be you are predicting a number that's too high. Sometimes you're predicting a number that's too low. Those should not cancel each other out. So if you predict too high the same amount of time as too low, your error is not 0. Your error is actually the absolute value of both of those. So usually we take the absolute error, not the error itself. And then if we have n data points in our data set, we'll calculate the average absolute error for all data points. So this is the simplest one. You can look at some of the components here, divide by the total so that you can get an average, summation, the actual value, the predicted value. So that tells you what I'm actually doing here. Any questions about this? This is one of the simpler ones. Okay. For all of these, I don't really care if you memorize the equation because there's a built-in function. What I do care is this bottom line here. So you should know what a value means. If I tell you the error is 0.5 meters, then you know, okay, well, the thing I'm trying to predict is the size of a vehicle, so that's okay. But all of a sudden, 0.5 meters doesn't sound so good when you're trying to predict the size of an atom, something very small. So it has the same units as y. If you're trying to predict temperature and you're off by 100 degrees, that's not very good. But if you're trying to predict the height of a building and you're off by 100 meters, that might be okay. So it really depends on the units, but smaller is always better. You're trying to minimize the error that you're making, the mean absolute error. Okay, another one that I would say is even more common, I think RMSE is probably the most common one I see for regression. Another one that's really common is root mean squared error. So the idea here is certain errors are worse than others. If I'm predicting the height of a building and I'm off by 1 or 2 meters, I really don't care. If I'm off by 1 or 2 kilometers, that's really bad and I really care about that. And it's not just like a little bit worse, it's like exponentially worse. So we can actually design a error metric or a loss function that punishes larger mistakes more than smaller mistakes. And we can do that by squaring the error. So small numbers become smaller, big numbers become bigger. As usual, we have a bunch of data points, so we want to take the mean over all of them, and that will give us the mean squared error. And then, of course, our error now is in these units of meters squared. We would really like to get back to our original units, so we can take the square root at the end. And here are some examples. So for these predicted values, you can see the mean absolute error is not really that bad, but the RMSE now you can see is, let's see, these are different scales. So yeah, it's still smaller. So now everything within that 0.01 range is almost ignored. It's almost getting close to 0, whereas everything above that is getting penalized more. Again, smaller is better, and RMSE, as long as we take the square root, the error that we're predicting is in the same units as our y. So meters, degrees, parts per million for CO2, whatever. Okay, the other one that's really common that you might have seen before is called this Pearson correlation coefficient. This is what it looks like for an entire population. So it's this expected value thing. You've probably seen this one instead. This is the R value that you see in a lot of plots. This tells you how close to the correct line of fit a prediction is. This is how you calculate it. Again, I don't really care if you memorize that. These values range from -1 to 1, and they're unitless. So the number actually doesn't have any physical meaning. It just tells you if it's close or not. So for example, if I'm looking at the top row, if there's really little to no correlation between my prediction and the correct answer, I have a R of 0. It's just random noise at that point. If I'm really good at predicting things, I'll have an R of 1. If for whatever reason I'm predicting the exact opposite, so every time it's big, it's actually small, I would get -1. -1 isn't really a problem. I could just flip all of my predictions and then it would become 1. So the goal is to get a large number, preferably 1, but -1's good too. 0 is bad. There are some limitations of this model. So for instance, if I look at the middle row, these are all 1 or -1. The 1 in the center is actually undefined, so your computer's going to blow up if you try to predict that. And then the bottom row, these are all 0. As a human, you can see there's patterns there. It's not random. But in terms of this equation, it can't tell the difference. These are all equally bad guesses. So this is not perfect. We're trying to take thousands of data points and thousands of errors, and we're trying to summarize them in one number. So you're always going to have loss of information. It just depends on which information you're losing. The other one that you'll see, and this one's becoming more common, I think, is this coefficient of determination. This is more about variance than it is about fit. It's known as R squared, and this is the formula. So the top is the sum of squared regression, and the bottom is the total variation in the data set. This one actually ranges from negative infinity to 1, so you can be infinitely bad, but you can only be 1 good. So 1 is perfect. If you just always predict the average answer, you get 0. If you're worse than random guessing, you get negative. And then if for whatever reason your y is always the same, you either get nan or negative infinity. That's usually not the case. It's very rare to train a model where the correct answer is always the same thing, but that could happen. Sometimes you will see lowercase r squared. Please don't do this ever, because it's really not clear if you mean the coefficient of determination or you mean Pearson's correlation coefficient squared. So usually that is just ambiguous. Don't do that. It's either lowercase r or capital R squared. This is where I did want to have a break, but we don't have a lot of time. I want to jump to classification. Regression was very easy. You're really just, there's only so many ways of measuring the amount of mistake you make. Classification is much more complicated, and there's a lot of different ways to measure error and accuracy. Okay, so we have the same goal that we had before. The difference now is our y is no longer a real valued number. It is a category, and there are a finite number of categories we're allowed to predict. Category 3 is not larger than category 1. They're just random numbers assigned with categories. There's no ordering involved in these categories. There's different kinds of classification. So you might have binary classification, where there's only 2 possible values, true and false, spam and not spam, -1 and 1. You might have multi-class classification, where there are many possible correct answers. And you might also have multi-label classification, where a single image, for whatever reason, could contain an image of a cat and a bald eagle fighting each other, because that's what happens in America. So all of these are different kinds of classification. You really do need to know which one you're doing in order to correctly make an assessment of accuracy. Multi-class is probably the most common, but you do see binary and multi-label from time to time. Also, when you're labeling pixels in an image, each one of those pixels might be binary or multi-class. Multi-label is a little trickier, but you could technically have like multiple things in one pixel cell. Okay. The other thing that I want to impress on you today is that not all answers are equally wrong. So some mistakes are more important than others. If we're only thinking about simple binary classification, these are all possible ways of making a prediction. So if I predict positive and the correct answer is positive, it's a true positive. If I predict positive and it's actually negative, that's called a false positive. Same for false negative, same for true negative. Now, I don't like to make you memorize, but I do want you to memorize true positive, true negative, false positive. Every other accuracy metric we will see today can be derived using these 4 things. So do remember this. Again, the total population is all of the positive and negative samples. So that's another useful thing. Okay. Yes, all other metrics can be derived from these. So the one that you've certainly seen before, the most common one, is just simple normal accuracy. Accuracy ranges from 0% to 100%. If we're doing binary accuracy, it's all of the correct answers, both true positives and true negatives, divided by the total population, the total set of questions. So if you get things right 90% of the time, 10% of the time you have a false positive or a false negative. We don't really know which. If I have multiple classes, I can also do the same thing. I can say, how often is my prediction matching the correct prediction? And then my accuracy might actually decrease because random guessing, if there's 10 classes, random guessing might be 10%, not 50%. So always think about baselines, always think about worst case scenario, what number should I get? And then when you do get a number, is it much bigger or about the same? That's really important. So simple accuracy is whether or not you get the right answer. Sometimes you might get close, and there are accuracy metrics like top K accuracy that also count that. So if I'm trying to predict one of 1,000 labels, and my top pick is wrong, but my second pick is right, that's better than if I was wrong like the first 10 predictions. So you'll often see like top 5 accuracy for certain things where one of the top 5 predictions was correct or was not correct. And that's more forgiving for a really challenging classification task where there's a lot of different classes, especially ones that are closely related. As K changes, you get different things. So if K is 1, you might see that all of them have relatively low accuracy, but as K increases eventually to the size of the number of classes, one of them's always right. But you can see that at any particular K, the best model might actually change. So you want to see, you might even want to try multiple values of K and provide accuracy metrics for all of them, how they change over time. Okay, so that was accuracy. This is the most common. It's also really easy to understand. Everyone understands percents. If you're trying to communicate to a non-scientist, you probably want to use this one. But accuracy is also really bad. And if you're trying to communicate to a scientist, you really don't want to use this one. And here's why. If we go back to that thing I posed in the beginning, Lyme disease, a rare disease that affects 0.1% of people in Germany. Let's say I want to develop a state-of-the-art AI model for detecting Lyme disease. Here it is. I have a function has Lyme. The input is thousands of dollars worth of expensive medical tests, and the output is true if the patient has Lyme disease, otherwise it's false. And it is hard-coded to return false. Let me ask you another question. How accurate is this test? What is the accuracy of this model if 0.1% of people are true?
99.9.
This model is 99.9% accurate, and it's only one line of code. Look, we've solved the problem. How useful is this test? It's not useful at all, right? This is garbage. If you tried to sell this to a medical company, they would say, "Are you out of your mind? This is useless." So accuracy is not always a good measure of usefulness because of class imbalance. When certain things are less common than others, accuracy becomes very useless. And usually, certain things are less common than others. So accuracy is usually useless. So how do we deal with binary class imbalance? There's actually several ways to do this. Again, perfectly valid response, collect more data. If you just keep collecting more and more data, then you don't have class imbalance anymore. If I have 100 people without Lyme disease and 1 person with Lyme disease, I just find 99 other people with Lyme disease, and we don't have class imbalance anymore, do we? So that's one approach. Another approach is weighted sampling. So if I have 100 examples from Germany and 1,000 examples from Spain, and I'm training a model, and I don't want the model to be biased towards Spain, I can either sample less often from Spain, so use a subset of the Spain data, or I can sample more often from Germany, maybe even repeat some of the data multiple times. And then I get more balanced distributions. And then the third option, which is what I'm going to teach you now, is different metrics that deal with binary class imbalance better. So the first one is precision. This is the ratio of true positives over predicted positives. This tells you if I predict positive, how likely is it that it is positive? That is a useful measure. We're completely ignoring false negatives. We're completely ignoring true negatives. Another one is recall. So now this is similar but slightly different. If the correct answer is positive, how often am I predicting positive? So this is a difference between do I just always guess true or do I just always guess false? So it really depends on these two ratios. These give you very different estimates of things. Another one that I see less often is fallout. This is the ratio of false positives over negatives. And you might also see things like this, where you have the ratio of precision versus recall with different thresholds. So if I'm making a prediction and I want to guess whether or not this image is water or land, I might have a prediction that's 0.3. And if it's closer to 1, then it's land. If it's closer to 0, then it's water. But I don't have to split exactly at 0.5. I could slide up and down and allow more false positives for the sake of minimizing false negatives. So it's not always just one number. Sometimes it's an entire plot with different trade-offs. Again, if you are making a prediction, for example, let's say you're testing someone for cancer. A false positive and a false negative are very different and they have very different outcomes. If I am trying to check if someone has cancer and the test has a false positive, that might be the worst day of their life. But when they get a second test that says, actually, no, it's negative, they're fine and they live. If I give a false negative and I say, no, you have no problems, they're not going to get that second test and it's too late by then anyway. So false negatives and false positives are not always equally weighted. Sometimes you might want to risk more false positives for the sake of fewer false negatives. If you see this ROC curve, it is just the trade-off between recall and fallout. And you'll also sometimes see this area under curve as another number that people predict. So there's a lot of different ways that you can split this up. The other thing that's going to be really confusing, how many of you are from like a GIS, geography background? Anyone? One or two? Okay. In that area, you probably know phrases like user's accuracy and producer's accuracy. These are the exact same thing as precision and recall. In statistics and medicine, we use sensitivity and specificity. Those were the things we saw when we looked at Lyme disease. In machine learning, we use precision and recall. Not one of these is better than another. They're all the same thing, but it's really confusing that we don't all use the same terms. I don't think that's ever going to happen. But if you see these terms, that's what they mean. They're all the same thing. It's just different domains use different words for the same fraction. Okay, so we saw precision and recall, and we said both of these are useful for different things. If I predict positive, how likely is it to be positive? If it is positive, how likely am I to predict positive? Those are two very different numbers. What if we want a single metric that captures both of these things? This is where F-scores come in. We can actually combine both of these numbers using a harmonic mean so that both of them have some weight in the final outcome. This is what that looks like. So if I have many different possible values, I get that ugly summation on top. If there's only two possible values, it's much simpler. So an F1 score would look like this: 2 times true positive over 2 times true positive plus false negative. Technically, you can have any F beta score and they get more complicated. I have never seen anyone using any F score other than F1 score. So F1 score is the only one you really need to know. But again, This is high when both precision and recall are high. It is low when either precision or recall is low. So you have to be good at both. You can't just be good at one or the other. It's very, very easy to get a perfect score on precision or on recall just by always guessing the same thing, but it's much harder to get both good. That means you have to actually know what you're doing. One other thing that you see sometimes is object detection. So now we're actually trying to locate objects of interest. If you have a self-driving car, those could be things like stop signs or pedestrians. If you are using satellite imagery, those could be things like ships or planes or vehicles. So if I'm trying to locate an object, how do I measure the amount of mistake that I make when I'm locating that? One of the more common ones is the Jaccard index. As usual with science, the person who first discovered this doesn't have their name associated with it. It's the second person who discovered it and published more papers. So this is one of those many things that has been discovered multiple times. And it's also maybe more commonly known as intersection over union. So this is the formula. If I have two boxes, the correct box and my box, I look at the intersection of those two, so the area in the middle of both boxes, divided by the union, so the total area of both boxes. And you can also use this for image segmentation, although I personally prefer precision recall F1 score. This has all been performance metrics for binary class imbalance. What about multi-class class imbalance? So now we're predicting many different classes, many different categories, and some categories are less common than others. This is a real example that I pulled out from the news a year or two ago. They were looking at facial recognition technology, and they found that it was 99% accurate for white male faces. So it's really good at identifying my face. For less common racial groups, and even genders, it is awful. So for black women, it's 35% accurate, the exact same model. So one number is not useful. If I just tell you the overall accuracy for everyone, it's probably 95%. But for certain people, it really sucks and it's really bad. Why? The model itself is not racist. It's not ignoring certain people. The model did not see a balanced training distribution. It was not trained on very many black female faces. In fact, a lot of the older models, they would just take pictures of the people making the model and train it on that. And guess what? There's a lot of white male engineers who are making these things. So you have to be very careful when you deal with people, but any kind of class imbalance in any kind of data set, make sure that you have enough examples during training, especially of these different groups, and also pay very close attention to accuracy on some of these less common groups. How do I deal with multi-class class imbalance? As usual, we can collect more data, so we can get a balanced distribution, we can get people of all different colors, or we can get forests of all different geographies. We can do weighted sampling, so we can look at less common examples more often, or more common examples less often, and we can also use weighted metrics for multi-class class imbalance. So how do we do multi-class accuracy? I mentioned before with this Lyme disease example, if I just take the accuracy on all of the data, our model has a 99.9% accuracy. It's not useful, but it's very accurate. This specific type of accuracy is known as overall accuracy. This is where you just take the entire data set, you calculate the number of times you got it right, you divide by the total number, done. So that's overall accuracy. Very bad if there's any kind of class imbalance. There is another strategy which is called average accuracy. In scikit-learn, they refer to these as accuracy versus balanced accuracy. In PyTorch, they refer to these as micro versus macro. So just associate these things with each other. The idea with average accuracy is we treat each group separately. So what is the accuracy for Lyme disease? What is the accuracy for not Lyme disease? then take the average of both. So now every group, even though some classes are less common than others, has equal weighting, and we would find that our model is 50% accuracy because it's basically just guessing. It's wrong half of the time for half of the groups. You can also do average versus overall, precision, recall, etc. But be very clear at which one you are reporting because they're not the same. You can also do weighted averaging, weighted metrics. So for instance, let's say I'm predicting cropland. Some types of crop might be more important than others. So there might be things like lentils or flaxseed that are relatively less common, but they actually have a larger economic impact. So maybe we care about these more if our goal is to understand the economics of agriculture. So depending on what you're trying to measure, you can weight things to match that. I've shown you a few accuracy metrics. There are many more. This is just the Wikipedia page for all of these. So if you find one, if someone tells you this is the negative likelihood ratio for my model, you should be able to look it up and say, oh, okay, it's false negative rate versus divided by a true negative rate. Okay, I guess that's useful. Now I understand what you mean. Now I know if this number is high, then that's a bad thing, or if this number is low, that's a good thing. So you should know what these kind of mean. You should know where to find them. You should know which things should be low versus high, but you definitely don't need to know all of them. I don't even know half of these. But I've shown you the more common ones, especially for machine learning. So those ones you will see quite often in papers that you might read. Okay. Now let's go back to our original motivation with Lyme disease. Let's find out the answer to this question. Okay, so we know we know three things. We know the prevalence, which is the ratio of positive cases versus all people. So 0.1% of the time, people have Lyme disease. We also know the sensitivity, which we learned is the same thing as the true positive rate. True positive divided by all positives, and that was 0.9. We also know the specificity, that's true negative versus all negatives. Now, our goal is to learn the precision, the probability of a true positive, given that the model predicted positive. So now we have all the pieces to the puzzle that we need. How do we solve this? We actually use Bayes' rule, which you might have learned before, and we use the law of total probability, and we get 3% likelihood that given a test that says I have Lyme disease, I actually have Lyme disease. So two of you, I think, were right, but that was just by random chance. So there's a couple big takeaways here. One is statistics is important, and if you don't know it, then you're not going to survive very long. And also, just because things seem very accurate does not mean they are accurate when you have extreme class imbalance. In this case, most of the time, people don't have Lyme disease. So therefore, even when the model says I do, it's still very unlikely. There's also one mistake that we made here. Can anyone spot it? If it was actually 3% accuracy, it wouldn't be very useful. The first semester I taught this, I actually had one biology student who noticed this. I am using the percentage of people that have Lyme disease in Germany. I'm not using the percentage of people who are bitten by a tick that have Lyme disease. So most people never travel into the forest, they never even see ticks, they never leave the city. If you get bit by a tick and it's there for a long time, you're much more likely to have Lyme disease than someone who is just a random person on the street who hasn't been. So that is one of the things that we didn't factor. I don't know the percent of Germans who have been bitten by a tick. So the true accuracy of this test is quite a bit higher than I've led you on. But if you just look at the numbers themselves, just because something says positive does not mean it is necessarily positive. So that was the point of this example. Any questions on any of these metrics?
Like this 3% data, that prediction is dependent on that, the fact that 0.1% of Germans every year have a rare disease.
Yeah, so this 3%, this is if I pick one of you
Yeah.
and I give you this test, even if it says positive, there's like a 3% chance that it's actually positive. If I poll only people hiking through forests, it's going to be much higher than 3% because they're more exposed to this problem. So that was the mistake in this math. Any other questions? I know there's a lot of different classification and regression metrics. I tried to highlight the ones that are most common that you will see most often. As long as you understand those, not at a mathematical level, but just at a is higher better or is lower better, and what are some usual ranges? Is 0 to 1 or 0 to 100 or 0 to 1,000? The other thing that you'll sometimes see is you'll sometimes see people report precision as 0.9 or as 90%. And they never really say which they're doing, so you just kind of assume that like if it's 0.1, it can't be like 0.1%, it must be 10%. But they never tell you which, and that's a little frustrating. But as long as you use it consistently, then it's fine. So if you're comparing your model to someone else's model, just convert it to percent versus decimal to match. Okay. The last thing I want to talk about today before I get to the homework is hyperparameter tuning. I showed you this definition earlier. Parameters, those are the things in the model that you can learn automatically. Hyperparameters are the things that you as a modeler choose. Some examples, I mentioned the SVM kernel. We haven't talked about neural networks yet. That's the second half of the course. But here's a pretty picture of a simple neural network. And things such as the width of your model or the depth of your model, the number of layers or the size of each layer, those are also hyperparameters. So you choose how big of a model you want to use, and then you train it. But you don't really know, you can't really learn which model size works best without trying all of them, unfortunately. Those are the modeling hyperparameters. There's also hyperparameters related to the training process itself. So if I'm doing gradient descent, how far do I move each time? That would be the step size or the learning rate. If I'm training with batches of data instead of the entire data set, the size of each batch, and then other things like regularization, where I punish the model for focusing too much on one thing or another. These are also all hyperparameters that I choose. This is a typical workflow that you might use for training a model. So I have my data set at the top right. I first split it into training data and test data. The test data is reserved just for the very end, just to get the final performance. The training data I use for cross-validation. This should actually be hyperparameters, not parameters. But basically, for a given set of, I guess, parameters or hyperparameters, if I already have a model that's been trained on my training data, I can do cross-validation. So I can do either a train-val split or that k-fold cross-validation. Both are fine. I can use that to learn the best parameters. At the end, this retraining step is optional. I could retrain the model on all of the training and validation data, or I could just only keep it on the training data. And then I do one last final evaluation at the end. So I'm training possibly multiple models, possibly on multiple different training splits with multiple different hyperparameters. I pick the best one on validation, and then I calculate the accuracy only once on test. Okay. Now, the next question is, if I try a bunch of hyperparameters, how do I know which one is best? And which one should I try? So I asked my first advisor in grad school, how should I do hyperparameter tuning? If I don't know which model size is best, how do I figure that out? And this was his answer. Try all of them. And if you can't tell already, there's infinitely many possible things you could use. So this is a really bad answer, but it's technically true. Like, you do kind of have to try all of them to some extent. there isn't really a good intuition you can use. Maybe if you've done this enough times, you know that like for this size of data and this complexity of problem, this model size might work better. But usually you don't really know, especially when you're learning out, you really do have to try all of them to some extent. All is too many, so usually what we do is we try certain ranges or values. So for example, if I'm tuning batch size, maybe I just try a certain number and I double it. So powers of 2, 32, 64, 128. Maybe for learning rate, I expect a much larger range. So maybe I'll do powers of 10, all the way from 10 to the negative 4 up to 10 to the negative 1. These are all completely valid. And this approach is known as a grid search because for each hyperparameter, I am trying maybe 3 different values. If I have 2 hyperparameters, now I'm trying 9 different values. If I have 3 hyperparameters, then I would be trying 27 different possible values. So you see how this becomes just a grid in space. There's problems with grid search. It's quite simple and easy to do, but one of the problems is that it's not always the case that both hyperparameters matter. So you might find that the hyperparameter on the top matters a lot, and if you're off by just a little bit, the error is much higher. Whereas the hyperparameter on the left, it doesn't really make a huge difference anyway. It doesn't really matter, maybe for this exact case, how big the batch size is. As long as I have the right learning rate, the model learns well. So it's not always the case that every hyperparameter is important, and grid search is like the worst possible thing that you could do for this. This is another way to visualize it. So let's say I try all of these x values. I try 10 different values of x1 and 10 different values of x2. For each of those locations, I will know the amount of error for that location. And that's it. I only know those points in space. There is some underlying distribution, and that's shown in blue and red lines, but I don't know this. I only know those points that I sample. So at the moment, let's say red is bad and blue is good. I am getting kind of close to this, this middle value here. This is probably the ideal value, but I don't know that. I just pick one of these 4 as being close enough, and I say that's as good as we can get this specific hyperparameter. But I've tried 100 different possible values, and I've tried all of them with equal distribution, equal probability. Again, there are infinitely many, and you might end up wasting time on hyperparameters that don't actually matter. In this case, and really only this case, it turns out that the dumb solution, just trying random values, actually works better than the structured grid approach. So in this case, instead of picking 10 values for x1 and 10 values for x2, I'll just pick 100 values for both. And I'll only specify the bounds within which to search. So now instead of saying 10 to the negative 4, 10 to the negative 3, 10 to the negative 2, I say any number between 10 to the negative 4 and 10 to the negative 1 with, maybe some kind of exponential probability or something like that. And what you get is something like this. So now what you see is we have the exact same number of points as we did before. We have exactly 9 data points. But instead of trying 3 different values for the y-axis and 3 different values for the x-axis, we've actually tried 9 different values for both. And we've gotten really lucky and we've hit a very low value on the x-axis, and the y-axis doesn't seem to matter much anyway. We can't actually measure that from this experiment, but that's the result of this. So this lets us try a lot more values. You might have problems where sometimes it samples the same value or very close by multiple times, so clustering. You might also have examples where it misses a whole region. So it's not perfect, but it does let us do a lot more possible combinations for the exact same cost as a grid search. And then you might get something like this where we happen to get lucky here, we got even closer to this specific value, but where there's large sections where we're not actually sampling at all, and we don't have an easy way to tell whether or not there was a good value there. So random search is usually a little bit better than grid search, unless you really do know that all of your hyperparameters matter. Usually only one or two matter a lot. Is this the best way? Random is still kind of random. Can we do a little bit better? Again, we can't do gradient descent. We can't just say, I tried this value, this was the error, go downhill until there's no error. Because these are on the hyperparameters, not on the parameters. So we can't really do this until the model is done learning. And this is kind of like a meta loss function. So we can't easily, we can't use any of the gradient information. What we can do instead is we can use what are called black box optimization methods, where instead of measuring the gradient at any one location, we just create a map overall of the distribution of probabilities. So for instance, we would try a bunch of random values at the start until we start to notice that a certain location in particular tends to consistently have lower error. So then we sample more and more in that location, and we build this large probabilistic map. With these, you can also get an idea of uncertainty. So like for certain locations where we've sampled a lot of different hyperparameters, we're very confident about the accuracy here. For other locations farther away where we haven't sampled very many, we're much less confident, but all the values we tried were bad, so we didn't waste as much time in those places. So this is really the best possible trick that you can use for hyperparameter tuning. In practice, everyone still does grid search because it's just really easy to do and they just don't care so much. So if you're at a big tech company and you've got a lot of GPUs and you don't care about how expensive it is to do 1,000 tests, just do 1,000 tests. If you are a student running code on your laptop, one of these smarter methods, even random, would be much better at finding the optimum values instead of grid search. So those are much more valuable, better use of your time. One other trick that you can use to save yourself time and money, when you're training a model, you might notice that accuracy increases for some amount of time, and then it starts to decrease. So this is a very typical error curve or loss curve for training versus validation. On the bottom axis, we have time, so how long you're training the model for, how many epochs. On the left, you have the amount of error that the model makes. When you start out, the model is making random guesses, so of course it's going to be wrong most of the time. But over time, you get better and better. Now, at some point, your model stops learning and starts memorizing. And so the training error will always continue to decrease. It might be noisy, but it's always going to keep going down forever until it hits 0. Whereas the validation error is going to hit that sweet spot, that perfect fit, and then it's going to start overfitting, it's going to start memorizing, and your validation error is actually going to increase. So instead of training every model for the same number of epochs, exactly 100 epochs, you could train it until the validation error starts to get worse, and then you stop. And that'll save you time, it's quicker, and it also prevents overfitting. There's a couple, again, hyperparameters that you can use to control this. So like I said, there's going to be a lot of noise here. These aren't going to be smooth curves. You might have one epoch where it goes down, the next epoch it goes up, the next epoch it goes way down, etc. So you can say delta, which is how much the performance starts to drop, so how much the error increases. Or patience, how many epochs in a row is it getting worse? So is it just one bad epoch, or is it the last 5 epochs in a row where it's just gotten worse and worse? You can control those to decide when to stop. So yeah, that dashed line is where you stop. Maybe slightly before that is the perfect fit. To the left of that is underfitting. The model hasn't really learned as much as it could. To the right of that is overfitting. It's starting to memorize instead of learn. The last thing I'll talk about, I think this is the last slide. There's this concept of ablation studies that's really, really powerful and really important for machine learning. When you're building a model or you're building a data set, There's a lot of things involved. Some of these models, especially the second half of the course, are really complex. You might be designing your own custom model where you're mixing and matching different pieces. You might have a data set with multiple different inputs. So you're adding in satellite imagery and weather stations and water, precipitation, things like that. And it's not always clear which of these sources of data or which of these model features are helping and which ones are helping the most. And for that, there is a concept called an ablation study, where basically you systematically remove one or two parts of your model or of your data set, and you measure how much this impacts performance. So this is really useful for explainability, but also just for justifying the weird Frankenstein architecture that you've developed in the process. So this would be an example. Let's say you have 3 different features in your model. Your model is just like someone else's model, except it has these 3 things added to it. Feature 1, if I get rid of that, it only drops accuracy by 1%, so it's minor, but it's important. Feature 2, if I remove that, I get 10% less accuracy, so that's really, really important. If I have all 3 of them together, I get 93% accuracy overall. So this is really useful if you want to make your own custom model. You'll also see these experiments in almost every paper. These can be used for feature selection. So again, if you've got a bunch of data as input, which data is being used and which data is most important. If I'm dealing with multispectral satellite imagery, which spectral bands are useful? Usually a smaller subset are most important, but adding more doesn't usually hurt. And then if you want to do like a custom loss function, a custom model, which ones are helping improve performance, which ones are hurting performance. Any questions on hyperparameter tuning, experiment setup? This is really important because if you don't know how to set up an experiment, you can't do research. And this entire lecture, like, I don't know why, but no other machine learning course teaches you these things. And this is really what I think is important. So you can design your experiment in different ways. And as a result, you will measure different things. You might be measuring the average accuracy. You might be measuring the accuracy on certain classes that are less common. You might be measuring the accuracy if you train your model on one place and you evaluate it somewhere else. And it really depends on what your goal is and what you want to report to other researchers. Okay, last thing to cover is homework. Here is your reading list. As usual, read as needed. These are mostly the ones I think are useful for the homework. I find scikit-learn's documentation on this to be really, really good. Like I frequently refer to this even if I'm not using scikit-learn. So I do recommend reading some of the explanations of cross-validation, metrics and scoring, hyperparameter tuning, etc. I think the last one's only useful for the extra credit, but that might save you some time. What is the homework? We're going to be doing classification. So the first homework was regression, the second one was clustering. This is the first classification one. We're specifically going to be investigating forest cover type. And then there's extra credit for geographic cross-validation that I'll show in a second. Next week is the pre-processing lecture. I personally think this is the second most important lecture in the course. And the reason I say that is because as a machine learning researcher, approximately 10% of my time is doing machine learning, and 90% of my time is getting my data ready to do machine learning. So this is by far the hardest part of machine learning. It's also one that no other machine learning course teaches you because it's very domain specific. So this is an Earth observation domain course. We're going to be covering all the pre-processing you need for this. If you come, it's useful to bring your laptop. We're going to be running a bunch of GDAL commands. So if you have GDAL installed, you can use that and follow along. You can also use some of the data you downloaded for the last homework and just play around with it when I show you examples. Okay, let me show you the homework. So this is homework 3. So this is a forest cover data set. This was collected by the USGS and the US Forest Service. It's got about 500,000 data points, but each data point itself is very small. And each data point is just a single pixel, a single location, where they measured things like elevation, slope, soil type, etc. The goal here is just to predict one of 7 tree species. So it's classification. There are 7 possible classes. As usual, they are not balanced, and that is what makes this fun. As usual, these are the only things you're allowed to use. And these are the things that I import to solve the assignment. So you can use anything in Matplotlib, anything in NumPy, anything in Pandas, and anything in scikit-learn. I'm specifically using these things. You see things like accuracy, balanced accuracy, F1 score, precision, recall. You know what these are now. These will be useful. Yep.
I have a question about how, when with the inputs, I found a scikit or I don't know, or pandas, whatever, a stack method. Am I allowed to use that even if it
Yes.
doesn't stay there?
Yes. Yes. You can use anything from scikit-learn, anything from Pandas, even if I'm not directly importing it. You can add extra imports, but only from these things. You can't import like Raster.io or GeoPandas or something else on this assignment, only these things.
Write it there or where we use it.
I think it's easier to write it here, but you can also put it wherever. But I do check that, so I will take off points if you add in extra stuff that makes it too easy. Especially like the second half of the course, I'll teach you like PyTorch, and then I'll teach you Torch Vision, and then I'll teach you PyTorch Lightning, and then I'll teach you Torch Geo, and these really build on top of each other. So if you just go all the way to the end, it's really easy. But if you go step by step, you actually learn how each part of the process works. So I'm trying to do things in a good order. So yeah, you can use any of these things. As usual, it's really useful to like look at the documentation for these, because then it will tell you like, oh, this is the thing that helps me download the data set. The first thing I need to do is download the data set. I can use that instead of writing a bunch of code from scratch. Yeah, okay. So first step, download the data set. You could click this link. You could also read the hints up above, and one of these happens to be useful for that. Again, familiarize yourself with the data. One thing that you'll notice with this data set, some of these inputs are not numbers, they're categories. And it's using what's called a one-hot encoding, where there's 10 different soil types, and only one of them can be true at a time, the rest are false. We'll talk about that in more detail in the pre-processing lecture, but if you do notice that there's one or 10 or 20 columns where it's either 0 or 1, that's what's going on. Pre-processing, we're going to do a train val test split, 60%, 20%, 20%. There happens to be a scikit-learn function that's very useful for splitting your data. You may or may not want to use that. For now, for the main homework, we're just doing random splitting, so don't worry about the details. And then maybe check the length of each split to make sure it's equal in val and test. The next thing I want you to do is just some quick statistics on the data set. What is the class imbalance of this data set? Are certain trees much more common than others? So what percentage of data points belong to each species? The hard part here is the hyperparameter tuning. So you're going to train a simple logistic regression model. You're going to use a one versus rest classification style. So that was the thing that I explained with the pizza versus not pizza. Choose 2 or more hyperparameters to experiment with and 2 or more values for each. So if you do a grid search, you might have 4 grid points or 6 or 8, I don't care, at least 4. Same for random training, so at least 4 different possible hyperparameter values. And this is the part where every single student loses points every semester. So we have a train val test split. You're supposed to train the model on the training data, validate the hyperparameters on the validation data, test performance on the test data. Every single semester, people just naively throw in grid search CV, which does its own k-fold cross-validation thing, so it takes all your data and mixes it up. Don't do that. If you look at the documentation, there happens to be a bunch of model parameters, and if you read about them, in particular, there's this CV thing that determines the cross-validation strategy. If you don't use this, you are doing 5-fold cross-validation, which is not what I want. If you give it a number, then it's for this stratified splitting thing. Either of these two things will let you have a predefined train and a predefined validation without doing this k-fold thing. You can use something like this, or there's a bunch of other ways to get this. But I'm hoping this semester more people will figure this out. It's really, really important to understand what's going on behind the scenes. Otherwise, you report an accuracy and you have no idea how you got that and no idea what that means as a result. So be very careful with that, but the rest of the homework should be relatively simple. Also, in this section, you're going to get thousands of lines of warning messages. Don't freak out. That's okay. So what's going on is basically the model has that early stopping thing built in. After a certain number of steps or epochs, it's either going to say, I maxed out, I got the best accuracy I could, and then I quit. Or it's going to say, I kept going for 100 epochs and it's still not getting worse. Just so you know, it might be underfitting. That's okay. You don't have to set the epoch size to be 1,000. It's going to take way too long. Just keep the default values and keep it simple and see which one is best given a quick amount of time. So if this is taking you more than 30 minutes, that's way too long. This should not take that long. It should take 5 minutes, 10 minutes at most. So don't worry about the warning messages. Also, don't increase the max steps or max epochs. I want you to calculate accuracy on the test set, report metrics for all of these. Last semester, a lot of people decided to calculate the confusion matrix and then calculate all of these manually by hand from scratch. And you always make a mistake if you do that. So use the built-in functions. They're very useful. Here, make a confusion matrix for all the 7 classes. I also want you to normalize it. So some classes are much more common than others. I want you to normalize it so it's the percent, not the just total number of correct values. But this will give you a very beautiful picture of how often you're getting the right class, and when you're getting the wrong class, which one and why. I've got some questions for you. What is the difference between overall accuracy and average accuracy? Which is more useful for this data set and why? So hint, hint, something to do with class imbalance. Looking at this confusion matrix, which ones have the highest accuracy, and how is this related to the class imbalance that you reported above? Extra credit. So this is geographic cross-validation. If I train my model in northern Colorado and make a prediction somewhere else, how likely is that model to work? I can test this by training it on different regions and testing it on unseen regions. So our data set is split into 4 different regions. I want you to basically repeat what you did above with a geographic split instead of a random split. So you're going to group all the data by wilderness area. Again, report class imbalance for these 4 areas. So you should notice that these 4 areas look very different. They contain different kinds of trees. Instead of using logistic regression, use a random forest classifier and use this leave one group out cross-validation strategy. So train on 3 places, test on the 4th place, rotate. People always miss this part. Just add like a comment somewhere explaining why this helps us achieve our goal of gauging accuracy on an unseen region. Report these metrics for each of the 4 areas, and then plot this ROC curve. You can reuse the logistic regression model if you want for here because it's just too slow to do all of them. Yep, question?
So we're using the same data as for the...
Yes, same data set. So you don't need to learn a new data set for this one. Any other questions? As usual, extra credit's optional. Do it if you have time. especially if you want to learn more. This is really, really useful for real research. Like if you want to really do research in this field, you almost always want to do a geographic split.
Will you upload the solutions of homework 1? Are we allowed to use that for this? Or
Which part of homework 1?
well, like will you upload the solutions of what we had to do, we would have to do, and then if you do, are we allowed to use it here?
So I'll show the solutions to homeworks after they're due in class, but I won't upload them because I want to reuse the same homework in future semesters. You can technically use things that you learned in previous homeworks on this one. This one's quite different because it's classification instead of regression. It's space instead of time. But a lot of like the data set splitting stuff and some of those techniques might be similar. And same on like the next homework. The next homework, there's also going to be classification. You can just copy and paste the parts of this that you want to reuse on the next assignment. That's fine. Any other questions on homeworks? I'll try to get you homework 1 grades soon. I won't have office hours next week because I'll be traveling, but feel free to email me and I should get back to you pretty quickly. I've already fixed a lot of bugs over email, so I'm always happy to help with debugging.
What is the timeline for project, when the proposal will happen and?
Yeah, so the project, don't worry about yet. The first project proposal deadline will probably be sometime around Christmas time. So I'll give you like half of the semester to see all the cool things that machine learning can do before you decide which thing you want to try to do more of. And then the midterm report will probably be like, not really midterm, like after all the homework assignments are due. And then you have another 3-4 weeks to actually finalize things and get good results. So I'll start talking about that maybe lecture 6 or 7. And I'll have it due during the break so that you don't have to do it at the same time as another homework assignment. So don't worry about that yet. Okay, I think that's everything. I will see everyone next week. Have a good weekend.